Yeah, today I'll be talking about how I prioritise compressed air projects and some of the concepts and tools I use to do this. I'd expect there to be light bulb moments for some of you. That compressed air projects, say a leak server that didn't give you the returns you were looking for, and you've been wondering why. Well, you might get the answer in this presentation. Most likely, the power saving was overestimated because the average specific power was used, not the savings yield taken from a power versus flow curve. Excuse me. I'll explain these terms a bit more shortly. So briefly about the Carnot Group. You can read what I've written there. The main point I'll point out is point 3. We aim to be the engineers in the corner of our customers' desks when they need help. We don't sell equipment. We don't take commissions. We don't generate certificates. So as we see it, we don't have a conflict of interest or ulterior motives. Our sole interest is helping our customers. And this also means that things like the compressor companies, they don't see us as a competitor, so they're more willing to share what's normally confidential information, which helps everyone with the work we do. Craig mentioned the compressed air guide. That's what it looks like. You can see the link for it there. I'll be referring to the guide off and on during this presentation. It was released back in 2017, and as Craig mentioned, both he and I had a hand in preparing it. So compressed air is a utility to support production. So when we come to set our priorities, our priority is to get production equipment working properly. Normally the customer's got a list of problems they want us to deal with. We then look to improve production rates and the compressor room reliability. And then there's energy efficiency work comes after that, but there's usually already been savings from the first 2 points. We start by logging the system at once a second, and that's important that it's that quick so we can see what the controls are actually doing and we can diagnose the problems. That data we then average to 3 minutes to better reflect what's actually being used by the system, not what the compressors are pumping into it. And if you don't do that, you end up with lots of blurry lines, which you can't make sense of. Any report must have a power versus flow or an efficiency curve in it. And the reason why is because it's the shape of that curve that certainly I use to prioritise projects. And it also feeds the economic arguments for any air saving work you do. So have a look at some of these sample curves. This top curve is a system before and after a compressor upgrade. The brown points there, I don't know if you can see my cursor. The brown points are the old system. The green points were my modelling of the flow with the new system before it was bought. And the blue points are the new system. Now, in later slides, I'll refer to this as being the ideal system for a variety of reasons, apart from the fact I designed it. The bottom curve is one of my favourites. You can see that there are basically 2 bands. These are 2 different compressors operating on different days of the week on the one system. And the thing to point out here is if you say look at 10 metre cubed a minute at a flow rate there, this bigger system was drawing 115 kilowatts and the smaller system was only drawing 54 kilowatts. Now, for the same flow rate, that's one compressor using half the power consumption of the other. So one's twice as efficient as the other. We then start looking at what happens if you reduce the demand on the system. And again, we say, look at the big curve. At 10 metre cubed a minute, we're using 115 kilowatts. If we're down at 5 metre cubed a minute, we're using 90 kilowatts. But hang on, we've reduced our air consumption by half, but we've only saved a quarter of the air. It's a quarter of the power, should I say. And this is where we see what I call the savings yield, which is your power consumption isn't linear with flow. It follows the curve of your efficiency curve, of your power versus flow curve. So for the big compressor, you can see it's 5 kilowatts per metre cubed a minute. For the smaller compressor, it's only 2 kilowatts a minute. So you might say, oh, we'll save more if we run the big compressor, but hang on, it's using twice the power. To complicate it more, for this survey, the average specific power for the system was 10.6 kilowatts a metre cubed a minute. Now, most people would say, okay, our average is 10.6. They think that's linear back to zero. So at our 10 metre cubed a minute, we would have been operating at about 106 kilowatts per metre cubed, and they assume that any savings are going to go back to 0, 0. But we can see from the savings yield plots that it's nowhere near that. It's maybe only 20%, maybe 50%, and you could save a heck of a lot just by running the right compressor. So with this system, they're already running one compressor one day, another compressor the other day. All they have to do is only run the little compressor and keep the big compressor as backup. They were running both just for the sake of equal hours. If there is a situation where they do need a bit more air, say above the 13 metre cubed a minute here, so the big compressor might run from time to time, that's when you do some targeted demand work to get the demand back below that 13 metre cubed a minute. So the little compressor only has to run. So some quick bit of some jargon. I won't go through all of this, but what I will point out is the high priority of condensate drains. Craig mentioned time drains blasting off left, right, and centre and water everywhere. There's some quick numbers there for Melbourne and how much water you use and why time drains waste air. If there's a time drain on the system, a high priority is to replace it with a no-loss drain, say a float drain, an electronic level sensing drain. The ideal system has actually got duty standby drains on it. Float drain is a duty drain, electronic drain is a standby drain, and we monitor the valve in the standby drain. So if it needs to operate, there's a problem with the float drain and maintenance can come and fix it. The points down below are bits and pieces of equations, but what they lead us to do is understand how much air is stored in the system each time a compressor cycles. So load, unload cycle, we're talking all flooded screws here. And the reason why we need to know that is because it then leads us into understanding the compressor system factor. Now, CSF would be novel for most people. Those that have read the guide would have read it. Those that have listened to me from time to time might have heard of it. What it is how much of a compressor's capacity is stored in the system each time that cycle. And you can see the equation there. And the beauty of CSF is it explains the shape of PVF curves. So you can see here, we've got a CSF7, curve for a CSF7 system, 14, 21, 100. You can see as you get a bigger CSF, so your curve flattens out, you get a better yield and your part load efficiency improves. This light green line across the bottom is a VSD machine, and you can see it's really efficient at part load, at trimming the system, but at full load, it's using more power than a fixed speed machine, and that's because of the losses in electronics and stuff like that. So you should never run or never select a VSD machine to be a full load machine. You should only ever select it to be a trimming machine. You're better off having a fixed speed machine as your base load, and this reinforces some of what Craig was saying about picking the right machines for the right function and having different size machines. The dashed dark green curve here is actually two machines on the CSF7 system. So instead of having a single big machine, you've got two smaller machines. And you can see that it's far more efficient than just having one big machine. Coming back to CSF, the beauty of CSF is it is a time-based unit. You can measure the CSF of a compressor in its system with a stopwatch. Very simple to do, very easy calculation. The guide, part 2 of the guide takes you through how to do it. There's worked examples. And that provides us a really good link between what's happening to your system in the field and any desktop modeling you want to do. We've got the equation above, which is how we calculate it at the desktop. From field measurement stuff, if you note the load unload pressures of the compressor, you can then work out what your wet volume is, and you can interchange between both sides of your modeling. CSF can be then used to model the part load efficiency of your system. So if you have a look at this curve, that's our favorite system again, and the round dots and the triangles are the model using CSF of the power consumption of the compressor. So you can see how CSF gives you a really good modeling, good way to model what your compressors are doing, regardless of well, not regardless, but actually taking into account how they're installed in the system and how they interact with the system. And what's really critical here is that it reinforces how the whole system affects the efficiency of how your compressors operate. You've got your wet volume, you've got your load unload pressure settings, you've got the pressure drop across your filters and dryers. Reduce the pressure drop across your filters and dryers, and you get a bigger effective storage in your dry volume. You get a bigger CSF. Your system efficiency improves because you've got better CSF. Plus, you can also lower your operating pressures because you've got that lower pressure drop. So you need to consider the whole system to make sure it's operating efficiently, and you need to maximize each of those components. While this is taught, these curves are about oil flooded screws, the same concept applies to other compressors. Centaks and centrifugals, not so much. As Craig said, if you get below the minimum turn down, they'll start to blow off, and then you'll have a curve which is just flat, and you can save all the air you like, and you'll just blow off more air. So there are special cases, but the technology and the concepts are still the same. So we start to look specifically at the curves. There's three main classifications for the curves. You've got the ideal curve, which is our ideal system I've shown here. It's a straight line, can be drawn straight through to 0, 0. So the savings yield is your average specific power. What sort of projects do you do here? Well, you reduce your demand, so you reduce the power that way. You can lower the pressure, which drops it down here, and maybe do some waste heat recovery work. The next curve that we look at is what I call a spoon curve, and it's called a spoon because it kicks up at the end. The top 20 to 30% is another machine running lightly loaded, maybe less than 40%. Now, what you can see with this curve is to the right of the step, you've got a really high savings yield. It's 9 kilowatts a meter cubed a minute. So it's really worthwhile doing any air saving work here to reduce that demand below the step, and you get a step saving if you get to the left of that curve. But once you get to the left, your savings yield drops off. So your priorities for projects have to change. You then come back to looking at how can I improve the CSF, which will straighten the curve out a bit instead of being domed and give you a better yield for any energy saving works you want to do. And lowering the system pressures will drop everything down and reduce your overall power consumption. The next group of curves is basically anything else, and you can call them domed. None of them go straight through to 0 on their curves, but there's three basic ways you can fix this. On the left here, settings and sequencing, working with your control settings, working with your sequencing. There's no capital cost to do any of this. It just takes a little bit of time. For the compressed air guide, pages 9 to 14, we'll talk about different sequencing actions and how to implement them. So a quick example here, this system you can see in the power versus flow curve, it flattens out as demand gets up. This system's got a VSD on it, but just because it's got a VSD doesn't mean it's got an ideal curve. And what's happening here is the pressures have dropped in the system as each new compressor comes online to the point that the pressure is below the target pressure of the VSD, and the VSD goes flat out. So it's not the VSD trimming the system in that situation, it's actually a 160 kilowatt fixed speed machine, very lightly loaded. What they should be implementing is the bottom curve, which is a centered control logic. And you can see that the pressure in that, which is the dashed line, is constant regardless of load. And the VSD, because its target pressure is between the load and unload settings of the other machines, is always loaded. The next way is what I've called one big wet side. What a lot of compressor companies recommend is actually having separate receivers and dryers and filters for each compressor. So separate wet side system. If you were to link those receivers, you've all of a sudden made all of that volume available to the compressor, which is trimming. So you've immediately increased your CSF, made your part load efficiency curve better. because you've then got air being averaged out between the two sets of dryers and filters. You've got lower wet to dry pressure drop, so you're storing more air in the dry side. And because the compressors can see what each other are doing, they're going to be able to coordinate better on their own pressure settings. So they're not, because you'll have pressure drop across the filters and dryers, create havoc between what one compressor sees and what the other one's doing. Pressure drop in a system, all too often when there's problems with a compressed air system, systems have grown, new capacity's been added, but the pipework hasn't. You get pressure drop, which stops the controls working properly. So if we look down the right-hand side here, this power versus flow curve, this system actually has a VSD in it, not that you'd know it. It's certainly not looking like a Nottle system. When we did this survey, we also did a pipe mapping exercise, and you can see the lots of pretty lines through the middle of that. There are actually 3 compressor areas on this site. And you can see the VSD in the bottom right there. What was happening was the biggest air demand was over at the VSD, and there's too much pressure drop from the other compressors to get it above its target pressure. So the VSD was running flat out, and it actually was one of the compressors in this half compressor room, which is trimming the system. So our modelling of the pressure drop between the 2 compressor stations there, you can see we picked up a really high pressure drop. So the project here was actually removing that pressure drop, let more air through from one side of the system to the other. The VSD compressor could start to trim again. But with all of this, the lowest cost is changing your compressor control settings. No capital, it's slight labour, which, okay, there's a cost there, but there's no new capital required. There's a little bit of capital to put a pipe in here, a little bit of capital to get rid of some of these pressure drops, but doing your controls work, there's no capital. So it's a very low cost option. Pulling some of the points together to make your system more efficient in the future. Here are some quick points that we've pulled out from the rest of the slide. With our ideal system, the compressors were bought to a specific function. There was a VSD, high efficiency VSD. There's a high efficiency baseload machine. The backup machine was almost as cheap, not quite as nasty as you could get. You don't need to waste money on tech for your backup machine. You are sizing your compressors for what they intend to do on the system. You don't buy a chainsaw to do the work of a hacksaw. You don't buy the hacksaw to do the work of a chainsaw. Same thing with the compressor. You buy the compressor to do what it's meant to be doing. As Craig mentioned, with your baseload machine, your smallest baseload machine needs to be smaller than the trim compressor, or else you will get control gap issues, as they're called. And as we saw earlier, the more and smaller the number of machines, the more efficient you are. It also means you can have a smaller trim compressor and your backup compressor will cost less. On your auxiliaries, insist you get no lost drains. Remote pressure feedback for the compressors. It stabilises your system pressure and corrects the wet to dry pressure drop. Big common wet side water volume, and go duties 2x-duty filters and dryers, so you get better reliability and better control of any water in your system. Once you've got your PVF curve as flat as you can, we look briefly at some demand side stuff. To me, I realised that any method of saving compressed air comes back down to one of 6 savings methods, and they're listed there with some examples. You can see here, if you've got a pressure gauge on a regulator, which is flicking around a lot, you've got poor regulation and you're wasting air when an actuator moves. So the sort of activities I'd be looking at is doing a regulator survey to make sure your regulators are actually properly set. Remember, with an actuator, it's the differential pressure across the actuator that does the work, not the supply pressure. So often people will have dialed up the supply pressure and then use the speed controllers to make sure that the differential pressure is right. You can go through and tune all that, and page 25 of the guide afterwards tells you how to go about doing that. More efficient devices. If you've got pipe nozzles, yes, you can replace them with more efficient nozzles, but you can also crimp them in the right fashion a little way back from the outlet to greatly reduce how much air they're using while still maintaining the same force. You can read about regulators and how they affect air consumption, and you can read about how to go crimping pipe nozzles. If you go to airbestpractices.com, it's a trade magazine in the US. If you search on my name, you'll find 2 or 3 of the articles that I've written for that magazine. And yes, on the demand side of things, there are doing air leaks. That's artificial demand, excess air on time, just turn things off. If you're going to do leaks, remember that the easy bit is finding the leaks. The hard bit is doing the repair management work. You'll need to allow 2 or 3 times the cost to actually manage repairing the leaks and doing the leak repairs than actually finding the leaks. So with that, thank you. Thanks for listening. I hope you realise how the importance of having a PVF curve for your system so you can prioritise compressed air projects for the best rate of return, and also so you know what savings yield to use for any demand side work so you don't overestimate the savings and so no one's disappointed by the results. Thank you.